Today I want to talk a little bit about the octet rule and some exceptions to it. So when you first learn chemistry at an introductory level, we teach you the octet rule. We say that everyone likes a full valence, and a full valence is 8 electrons. And 8 is kind of a magic number in chemistry, and there's a lot of truth to that. The 8 kind of groups, for main group elements, and the periodicity that we see on the periodic table in periodic kind of chunks of 8 is all very true. It's all very useful. But when students learn the octet rule, they hold on to the octet rule, and they have a hard time letting go of the idea that there are some exceptions to it. So I just want to do this quick little video to talk a little bit about some of the exceptions to the octet rule, just so that you won't be shocked by it as you're looking over different compounds and as you're seeing different options here. So when we're talking about an exception to the octet rule, we're talking about fewer or greater than the 8 valence electrons that the octet rule suggests. Right, it's right in the name. I would say that the octet rule is really more of a guideline, because what it says is that it's happy, that elements are happy kind of from an energetic standpoint with a full valence. And so 8 valence electrons is a full s and a full 3p orbital set. So that's usually what we talk about with our valence electrons, but there are things that are just as comfortable kind of from formal charge standpoint, from an energetic standpoint, from a sharing of electrons standpoint, with either fewer or greater than 8. And some key exceptions to that would be the metalloids when they're acting as molecular compounds, so when they're acting as nonmetals, and because of shifty d orbitals that cause kind of weirdness and allow for greater than 8 valence electrons in some of our covalent or molecular compounds. So let's look at a couple examples. Let's take boron trihydride first. If I'm doing the Lewis dot structure for boron trihydride, I'd say, okay, well, I need the total number of valence electrons. So the total number for boron is 3, based on where it is in the periodic table. It's in column 3A or 13. And so its valence electrons are the 2s2, 2p1. Those are the highest energy electrons. And then I have 3 hydrogens, and so I know that there are 1 valence electron in each of those. And when I add those together, that means I have 6 electrons total to work with on my entire structure. Now that's already going to be a red flag that this is going to be an exception to the octet rule, because I don't even have a full octet there. So what I'm going to do is I'm going to follow my pattern. I take my boron and I attach everything else to it. And I choose boron at the center instead of the hydrogens because it wants to make more bonds. And now I've used 2, 4, 6. That's all. I don't have any more electrons. This is the only way I can fit this together. And I would look at this and analyze this and say, but boron doesn't have a full octet. But that's okay. I have a lot of students that try to add a lone pair there. You can't add a lone pair because there aren't the electrons to do so. So this metalloid at the center of this covalently bonded compound is happy with 6 in its valence. It's an exception to the octet rule. Now let's go a little bit further up the periodic table. If we take phosphorus, there are 2 ways that phosphorus and fluorine, or phosphorus and any of the halogens for that matter, like to pair together. So it likes to either be phosphorus trifluoride, or it likes to be phosphorus pentafluoride. So let's look at the difference between the two. So if I take phosphorus, that's 5 based on where it is in the periodic table. And each of my fluorines has 7. So 3 times my 7 is 21. That gives me 26 electrons to work with. My phosphorus is going to be at the center. So I've used up 6 in just bonding my fluorines to that central atom, which gives me 20 electrons to have as pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I've used up 18 on my outer elements, so that means I have 2 electrons left over that I can put on my central atom. Now if I'm analyzing this thing and looking at formal charges, fluorine has a full octet. It has 7, it wants 7, has 7, wants 7, has 7, wants 7. Phosphorus has 1, 2, 3, 5, and a full octet when I take the shared ones into account. So this would be a Lewis dot structure that really jives well with the octet rule. This makes sense. This is what it looks like. I'm not surprised by this, but what would be shocking is if I tried to put more of these fluorines around, like in my phosphorus pentafluoride, which is another common way to stick these guys together. So let's look at these. How many electrons do I have? I still have the 5 from my phosphorus, and then I have 5 times my 7 for my fluorine, which is 35, so that gives me 40 electrons total to work with. So if I put phosphorus at the center and I attach all 5 of my fluorines to it, then now I've used up 10 electrons just in the bonds there. So now I have 30 electrons to play around with and put as pairs around my outer atoms. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So in putting those around in my 5 atoms here, I've used up all of my electrons. None are left over. Now if I'm analyzing this, I would say, well, this looks a little bit weird because phosphorus here at the center has 1, 2, 3, 4, 5 shared pairs of electrons, which means it has 10 in its valence. All my fluorines look pretty happy though. And if I'm doing my analysis on this in terms of formal charges, phosphorus has 5 valence electrons, and here in this structure it has 5 valence electrons. So this would have a net 0 formal charge as well. So this is a valid structure. It's something that will form, and it's just another way to look at these things. We start getting these greater numbers, and students kind of panic, and they try to attach rows of fluorines onto the phosphorus and all sorts of wackiness. Stick to the pattern, stick to the symmetry, follow the rules, right? Figure out how many electrons that you have, then stick everything else to a central atom, then put the pairs on the outer atoms, then you can put any remaining pairs left over on the central atom. So long as you follow that pattern, whether it breaks the octet rule or not, then you're always going to end up with some valid structures, and you can check the validity of those structures using your formal charges. If you have any questions about any of this, don't hesitate to reach out. Otherwise, I will talk to you again soon.